Okay, hello to you all. I want to wish a warm welcome to our today's lecture and to all of you who are here in front of myself and in front of Institute for Philosophy and Social Theory. This is probably the first time that we have a guest lecturer here who is actually a theoretical physicist. I mean, who is in theoretical physics, but we are moving the boundaries of conversation and communication. So I hope this will continue. You probably read abstract and about our today's lecture. He works at the University of Luxembourg. He's from Bologna. He's really much into the promotion, not only theoretical physics, but the promotion of science and the influence that scientific discourse has on society. So he will talk a lot more on that subject. So I wish to give my word to him. And now, Matteo, please, you can take over.
Thank you very much, Alexander, for the invitation. It's really it's great to have a chance to meet philosophers and people from social theory and to confront. I'm a bit excited and nervous, I must say, because I never actually talked in front of such audience. So let's see what I can do. I hope that we have a very interactive conversation. So please feel free to ask questions in the chat. Interrupt me anytime. I will try to follow and also make some proposals, because as Alexander said, on the one side, I'm a theoretical physicist. So I do my research in thermodynamics in a modern fashion. But I also spend a consistent part of my time trying to think about new forms of conversation about the relationship between science and society. And these projects very much involve social sciences, anthropology, sociology, philosophy. And so for me, it will be a great occasion to hear from you. Also, I'm in a beautiful countryside place full of animals. You will hear birds and cats and dogs and everything. I hope this does not disturb too much, but it's part of the experience, I would say. So now I will share my screen for my presentation. Let's see if this works. It worked before. So you're seeing my screen, right? Can you confirm?
We do.
Okay, so the title of my talk is Thermodynamics Between Science and Myth. I know this may be a very controversial title, especially if I talk with my fellow colleagues, scientists, who don't like to see the word science associated to other words that have a more mystical acceptation. But so I'm not, of course, I say this disclaimer from the start. I'm not saying that thermodynamics does not work as a science or that the second law is fake in any sense and then we can just do anything that we want. But of course, I want to deconstruct some aspects of thermodynamics that I think are special in respect to the construction of scientific facts that philosophers and social theorists have been very good at pinpointing. But sometimes this has been done with a little bit of, scientists are a bit scared of this kind of discourse. So we have to be a bit precise on what we mean by the words that we use. So I will try to be precise. And okay, I also pinpoint my double affiliation here. One is the University of Luxembourg, which is the official, of course, affiliation, where I do my scientific job, but I also conceive of this extemporanea, which is a collective of people with whom I'm running these projects on scientific conversation. And this is an open community, and I also conceive of it as one of my informal affiliations. So let's jump into the subject. The the first topic is into the vacuum pump. Now here I refer to, there's a very nice book by Scheffer and Chapin, Leviathan and the Air Pump. And in this book, they pinpoint, and also there's an interpretation by Bruno Latour, I think many of you may have heard of him, in We Have Never Been Modern, which starts from an analysis of this book by Scheffer and Chapin. And basically, they pinpoint the discussion between the period where Boyle versus Hobbes posed the foundation of what a process that we could call the purification. This is in Bruno Latour's words. So the idea is, at the same time, Boyle constructed the vacuum pump. So it's basically, well, not him, but of course the technology was available at the time, and he realized this idea that you could use the vacuum pump to produce pure facts of nature. So he invited the royal, he created, I think he was among the proponents of the Royal Society of Sciences in London, to invite these gentlemen to just observe pure facts. So it could be into the vacuum chamber, something could happen. So for example, it could be a candle, you know, that stopped burning, or something falling, or a frog dying. And he would claim that these were the pure facts of nature, completely removed from construction and social context, okay? At the same time, Hobbes postulates in the Leviathan society as a social contract between the individuals, each one interacting by a sort of contract with the state in an exchange of security for liberty, right? I'm making this, of course, very short, but the interesting point is making here there is a turning point, which is at the start of modernity, when by similar processes, which is the identification of some pure elements, on the one side the individual citizen, and on the other the pure facts of nature and society get divided. And this initiates the modern conception and the modern of science on the one side, and of the law on the other side, okay? So this is this is the starting point of modern science, but that has been already been there for a long time. If we think about mechanics, for example, the early theories of celestial mechanics. Wait. So people observing stars and their movement, and trying to figure out patterns. Well, we can see that there is a process of purification, in the sense that among the many phenomena that happen every day in the world in front of people, only a few can follow strict rules. And so at the same time, you define a domain where things work. So this is purification, defines the domain. And then once the domain is defined, so for example, the stars, within that domain, it's possible with some degree of precision to find laws, okay? And we have many examples of this, and this is the founding block of physics. So mechanics starts with ballistic, heavy objects floating in air, and you can predict more or less how they move according to the law of acceleration. Celestial mechanics is a very well-defined experimental setup which is fairly isolated from external disturbances. Or you can think of modern quantum mechanics, and in that case, again, you have to find very purified zero temperature vacuum situations where you can observe this phenomena of quantum coherences that are so fundamental for the theory to actually call it quantum phenomena. So purification, in a way, is you're trying to isolate a system. However, it will always be impossible to completely isolate a system from the environment. But at least, ideally, that's the tension. That's where you want to go. You want to isolate as much as possible the system from the rest of the environment, from external disturbances. And then within that system, somehow, as a projection, there are some physical laws, right? Some of these laws, for example, entail conservation of energy. So energy is a very subtle concept. I will not go into this, and I don't want to discuss how complicated it is to even conceive of it. But what's important is that the laws of mechanics, of celestial mechanics, of ballistic, of electromagnetism, of quantum mechanics, and of many theories that work in this idealized purification concept, they tend to have a very mathematically appealing form, and they come as theorems at some point. At some point, it's really that gravitational energy becomes kinetic energy, and this gives you recipes to calculate, for example, a trajectory of bodies. Okay, I'm making this very short. I will check. Are there questions already, or should I just go on? I would like to have some input every once in a while, just to know that I'm not talking alone. Anyway, let me go. Okay, from this, then physicists tend to assume, and this is, of course, a big philosophical step, that given that we find very beautiful laws in this projection to purify systems, then there is this assumption that all of the universe is just made up by adding these layers one on top of the others, you know, stripes of reality, until all of reality is sort of covered, at least in principle. We all know this is impossible in practice, because it's just too complicated. But this is an assumption that underlies most of the sciences ideology. Is like, yeah, we know we have chemistry, organic chemistry. Then we have inorganic chemistry, which is based on the periodic table, and it has very precise rules for how things combine. And we know a lot of it. We can do it in laboratories, synthesize stuff, etc. And then we have organic chemistry, which basically uses the same jargon, the same language, the same concepts, and of course also many of the same rules. But then if you try to actually reconduct or match the two sciences from a practical point of view, or you try to understand how much you can go from one to the other, you realize these are pretty separate domains of research. They have the same concept, but they don't talk so much one with the other. It's not that there is one patch that covers everything. There are patches of knowledge here and there, and they overlap. And when they overlap, often it's just because they share the language. Okay, But of course, one could argue, physicists would argue most often, that this is just because of technical problems. We can do it, but in principle, it can be done. And I don't want to argue with this. It's interesting because this is a strong philosophical assumption, which is not often discussed. But okay, one of the consequences that often happen when one confronts with with closed systems, isolated, purified systems, is that the notion of time disappears. If one tries, as I highly suggest this very nice article, Julian Barbour, The Nature of Time. You can actually skip, he has ontological considerations to make. He actually concludes that time does not exist, which I'm not interested in this kind of conclusion, because he believes the possibility of purifying everything, the whole universe in particular. But the way he describes how measuring time has been built in the history of humankind is extremely beautiful. So if you start from ancient Greece, what is time? Time is some periodic motion which is more stable than your own periodic motion. So you have a human being, and here, this is not a very nicely drawn human being, but he has some internal motion, of course, right? We can measure time by the heartbeat, for example, but of course, it's not a very precise measure of time. So we have to look into something which is bigger and more stable. So we can look at the sun, at the moon, and then we can build clocks based on those. But at some point you realize that also this is not a precise measurement of time if you want to be precise enough. Then you have to sort of get one step further. You want to go into maybe the whole Milky Way galaxy and take that as a reference. But then, okay, there may be experiments in astrophysics or cosmology where even the clock that you can build by confronting with stars will not be precise enough. So maybe at some point you will have to conclude everything, right? The universe, whatever that is. So this is on one side. On the other side, you can go into another direction of purification. You can go microscopic. So you can look into, the cells, and then into the molecules, and then you can look at the atoms with their orbitals, etc. And then you can build atomic clocks, more and more refined based on quantum mechanical effects, etc., etc. So, but again, if you have to do an experiment at this level, you need a more precise clock. If you need to do an experiment at this level, you need a more precise clock, and this ends forever until you get into the very tiny details, the ultimate details. So in a way, in both directions you go, you realize that if you really wanted to have a precise clock, you would have to measure everything, the whole universe. Everything should be included. But if the whole universe is included, then the universe becomes the clock of itself. And then there is no time, because there is nothing external to compare with. Okay? So these are very well-known paradoxes. So if you, for example, take a look at what happened to loop quantum gravity. It has been a famous program to quantize gravity. You will see one of the problems that they have to face is that they cannot make sense of time because they want to describe everything. And then if everything includes everything, then there is no evolution. There is no possibility to define something against which measure time. Okay? So these are just a few of the conceptual issues and hurdles involved in this idea of purification. It works for many practical situations, but if you push it very far, it leads you to some paradoxical situation, which is at stake with what we conceive of our own world. So now let's take a step back, because of course, then we know we are in the real world. Not everything is pure and purified. Not everything works mechanically perfect, but there are frictions. There is dissipation. There is energy which is not being accounted for. And now a little historical note is the following. With this group of scientists and philosophers with whom we are trying to have conversations on science, we're also reading books together. One of the books we're reading right now is this classical, I think many of you will know it, is Feyerabend Against Method. I mean, it's a light book. It's quite simple. We can understand it. There's less conceptual hurdles than in Lacatoche, and it also is fun. An interesting chapter is the one on Galileo, where he shows. No, we have this storytelling that Galileo came up with these discoveries and he overthrew previous paradigms, and everything worked, and it just was the church was against him. But if you actually go and try to reconstruct how the arguments that Galileo was using, and in general, what was the cultural situation where it was, where that kind of experience of knowledge was framed. And for this, I highly suggest this classical book by Paolo Rossi, Philosophers and the Machine, which tries to convey some of the social environment within where Renaissance and eventually the scientific revolution, so to say, happened. Well, if you go into it, you realize that there are a lot of hidden assumptions in Galileo construction. There is discrepancy between experiment and observation. There is a lot of fixes, which makes it so in the end, actually, the theory that Galileo was proposing, the observations were not more or less valid than what he was opposing to. It's just that historically he won, and a posteriori we started following that path and reconstructing why it made sense. But when he was there and when he was doing things, it was a patchwork, right? And one of the things that Galileo had to throw in is that when the moment he says, okay, I have an object, I give a force into it, and of course, according to Aristotelian physics, this would imply some velocity, but it said this implies some acceleration, right? I hope this is clear for all. But then this is in stark contrast with everyday experience. And then to make sense of it, Galileo has to introduce the notion of friction. So friction is something, and it's interesting because there is no explanation to friction. Friction is not included into the theory. It's just a ad hoc assumption that he has to introduce to make the theory work with what he wants to show, right? So, and friction will not be explained. There will be no physical explanation for friction until the late 18th century, because friction basically is based on electromagnetism, and we have to wait a long time before we can make sense of it, right? So the point is, the friction between the previous concepts and the new concepts, the new scientific revolution that Galileo is bringing, is also relies on friction as an ad hoc assumption that has to be used to make sense of things temporarily until some better explanation will eventually come in the future. And now I don't actually know if there is a story linking friction to heat. It would be very nice to actually research on this, if there is a continuity of ideas in the modern science. But the point is, friction belongs to this category of concepts which have to do with dissipation. And dissipation means systems are actually never isolated. They are never alone, and they always interact with an environment, and there is something which is lost in the equation of conservation of energy, for example, that works so well for stars, that works so well for nuclei. But if we are in the real world with macroscopic systems, there is something lost, and that something does not fall into the same categories that we use to think of other physical systems. And interestingly here, so what is heat now? So as I said before, for example, mechanics is based on energy conservation. Okay, so for example, kinetic energy plus potential energy, which is total energy, this is a constant. And then you can use this, you know, if you know, for example, how the potential of the gravitational interaction works, you can use this to predict the motion of bodies. But now if you introduce friction, because in a real world, energy is not conserved, then you have the first law of thermodynamics. I will put law in commas, which is now that work plus heat, and I'm going to write this like this, is a differential of energy. But the point is that this is not the same kind of law as this. This is a theorem where things are defined. This is defined, this is defined, this is a constant. And then if I know what this is, for example, if I have a theory of how gravitation works, then I can predict how the motion goes. But this thing is different, because this is actually the definition of heat. This thing is not defined in an independent manner. Heat, this is heat. And it comes from where I came before, is because it's just, it may be some new form of friction. It's just something that is not accounted for yet by a theory, and it may never be. And it's interesting that even though we know that heat is not exactly the same thing as energy, because it doesn't have an independent theory, we still, because probably it's just the way we use our natural language, which is very much object-oriented, we still interpret this thing for a long time as some quantity, something that exists, that is there, and that can be measured, quantified, put in a balance. So, for example, the history is full of pseudo-concepts that have been embraced and then abandoned about what heat is. So the theory of phlogiston, the theory of caloric, all of these have been thrown into the competition to try to explain what heat is, and then at some point abandoned. And they both resemble energy. It's just, they are energy in a way, but it's just that energy works because we are in a purified, at least ideally purified context, while these are the analogs of energy in a non-purifying, everyday contextual concept, and they just don't work. They lead to inconsistencies. They lead to things that cannot be this way. So that's the reason also I wrote as title here, dissipation and dissipatons. This is because physicists like to, especially in 20th century physics, we interpreted everything as in terms of particles and particle wave duality. So everything became something like, we have the photon, the phonon. So when you have this dissonance, it means that you can interpret it as wave particle. Okay, and of course, dissipatons don't exist exactly in the same way as photons exist, and nobody uses this word. What I'm just making the point is that we have a tendency to still try to fit things that describe processes into concepts that describe given amounts of quantified substance, which is not a process in itself. Okay. If there are questions here, I may have been talking already too much. I can stop a second or just go on. Okay.
We'll have time for discussion afterwards. So
okay. So breaking the wave. What is here? So what my point here is that thermodynamics which is the science of I could say it's the science of energy allocation. In a way, that can be many definitions. I don't want to choose one in particular. But what I want to say is thermodynamics has never been modern. There is something intrinsical in thermodynamics that does not allow to think of it as in an idealized way as mechanics, quantum mechanics, celestial mechanics, electromagnetism can be thought of. Even if we know that this purification process does not work. For example, in quantum mechanics, we know very well that there is a problem of measurement. But in any way, there is a tension. There is at least people try to purify things. Then they come up with the point that it's impossible. But that is the tension, which leads to these mathematical structures. But thermodynamics is not this way intrinsically, because thermodynamics, by definition, has to have to do with things which are not purified, with things in the world. It has to do with machines. It has to do with the quality of energy, of doing things with energy, doing things in a better or worse way. And from the technical point of view, I cannot go very much into detail of this, but the point is, when I was saying before that the energy conservation is a theorem in mechanics and it becomes a definition in thermodynamics, this basically applies to every thermodynamic concept, meaning that with thermodynamics, we cannot think of describing the whole universe. Let's represent the universe as a box. I don't know if that makes sense. But by definition, thermodynamics cannot apply to the whole universe. Otherwise, there is no time. Otherwise, as we will see, there is no entropy. But thermodynamics has always to do with some portion of the universe. And now the problem is, how do you define, so let's call this system, how do you define a system? Because there is no intrinsic special nature of systems with respect to the universe. There is no particular way of tracing the boundary. This is a choice that one has to make. At some point, one says, okay, this is relevant, this is not relevant. I decide to cut this stuff. And when you cut this stuff, something in between gets lost. And the two things, the universe and the system, they stop obeying the same laws of physics. They go into realms where even if you use the same words and you use the same framing of a law, the law does not do the same thing. So the first law of thermodynamics is a definition, while the first law of mechanics is a theorem. That's an example of this. And the point here is that whenever you have some quantity, let's call it A, of the universe, but at some point you want to split it into some quantity of the system plus some quantity of the environment, and you want to be able to say something about this, you're actually also adding there's some quantity of the observer, which embodies his choice of how to cut the system from the universe, and this is just thrown away forever and never to be seen again. Okay, and then you see when you do this, you are creating an asymmetry between the description you had before and the new description. And this opens up new possibilities, but also creates a completely new way of doing things, which are not in a different world. Okay.
Oh, sorry for interrupting. You have a question in chat.
Okay. Oh, interesting. So when I talk about universe, I'm trying, okay, we should talk with the universe with big U. So like the big U would be the universe where we actually live. And a universe with small u would be the ideal set of all things that exist, right? I don't know if it even makes sense to differentiate between these two things, but yeah, I'm actually here not trying to make a discourse about cosmology, but it's true. If one wanted to actually confront with thermodynamics of the universe, you additionally have this problem that even defining the boundaries of the universe is critical, because we don't even know if the universe is closed or open. It could be closed. It could be, you could think of a sort of sphere that grows like this and it's closed, or it can be a sort of hyperbolic plane without boundaries. And we don't know that. And more of a practical problem in cosmology. When I talk about the universe, I talk about a really idealized thing that just includes everything, which I mean, I don't think it's a useful concept, actually. I'm trying to avoid, but I have to go through it because that's what people use physicists use in their discourse. They always refer to the universe. Okay, I hope this answers a little bit. Okay. I'm trying to make, and this is okay, just a little technical thing is when I wrote the first law here. So see, here I wrote dE. This is a D. We use this to mean differential, which means that this is some A1 minus some E0. There is an energy of which this is the increase, okay? But then, even since the beginning of thermodynamics, people realized they had to write this not as a D something, but just delta Q. But there is no Q, of which this thing is Q1 minus Q0. And this is reflecting from a mathematical point of view, just the fact that it doesn't make sense to use concepts as objects like phlogiston and caloric to describe increases of this thing. So we call it an increase of heat. Heat as some amount that increases, but there is nothing that increases by that amount. And that is precisely because heat, for example, as it flows from here to here, there might also be a little bit of that flows into here. And this is, by definition, not observable, not inside the realm of application of thermodynamics. So we are in a different situation, okay? Okay, furthermore, thermodynamics has to do with the quality of energy. So basically heat is just an amount of some sort of energy that cannot be used again, that is of worse quality. But what is quality? You know, it's strange to use the word quality in physics because we are used to think of quantity, right? Quality seems to be a very qualitative concept, a very subjective concept, and it is. What if tomorrow I find a device that can use energy in a better way? Then the quality of that energy changes, and then the definition of heat is new, is different because it changed quality. It was a bad energy before, but now maybe it's a good energy. Or vice versa, you know, we have been using certain sources of energy thinking that they were clean, and then we realized they were not. So we constantly update our judgment on what is the quality of energy. And this is a very subjective process, which seems to be in stark contrast with the idea that physics has to do with quantitative, well-defined stuff, okay? So, okay, I will not go through the whole history of the concept, but to try to quantify the quality of heat, some people came about with the concept of entropy, okay? Which is some measure, in a way, of the quality of energy, of the loss of quality during a process, okay? Here, historically, it's interesting because thermodynamics starts with the Industrial Revolution, and then following these amazing technical achievements, people in academia started to, you know, trying to conceptualize it within the mental framework they had. So the framework was that of energy, etc., etc. And Rudolf Clausius came about with this concept of entropy and formulated this law that the entropy of the universe cannot decrease. But so now I want to a little bit to demystify this sentence. I think Clausius, this sentence in particular, but his own work is very detrimental to our understanding of physics. We should really give up with him. We should abandon him altogether, and even this sentence, for the following reasons. I tried. So let's go back to this problem, the entropy of the universe. The point is, I just claimed that thermodynamics is intrinsically involved with subsystems. So it doesn't even make sense to talk of the universe, to go back to the universe. If you actually try to expand the concept of entropy and apply it to isolated systems, then what happens is that the entropy increase for an isolated system is zero. The entropy of the universe is a constant. And if you actually believe that the universe has only one state that only occurs once and in some fashion, then the entropy of the universe is 0. So not much interest here. And in general, thinking of the entropy of the universe leads to paradoxes. So, for example, going back to the cosmological perspective on the universe that we have, we now think that the universe comes out of a Big Bang. So initially, it was a very hot ball of quark-gluon plasma with some very high temperature, T. Then there has been this explosion. And then at some point when the nuclear forces, which are very strong, settled down a little bit and things started to cool out, then the gravitational force kicked in. So we have, nuclear forces up to some time, which are very strong, electromagnetic forces, etc. And then at some point, finally gravity, which is a very weak force, sets in. And then gravity has ordering power. So gravity creates structure. It creates galaxies. It creates formations of stuff, planets, etc. So if we look at the history of the universe and with this idea that entropy, that there's another famous way of putting entropy as a measure of disorder, then the universe was a very, very, very disordered thing at the beginning. And then it has become a more and more ordered thing through the universe. So actually, if we buy into the idea that entropy is a measure of disorder, then the entropy of the universe has been decreasing since the beginning of time. Okay? Okay, so this is all very paradoxical. What's the problem here? The problem is just it doesn't even make sense to talk about the entropy of the universe because, as I mentioned before, entropy is about taking some system, making a claim that there is some reasonable way to separate this system from the rest. And this way of separating the system from the rest must be stable, at least in time, it must make sense, at least for the duration of the experiment that you want to propose. And then you can make a claim about something here, okay? So entropy of the universe demystified, but incredibly, of course, I don't want people to believe that the second law does not hold. I'm just trying to convey the idea that the second law does not play the same role as a law as other laws of physics do. But it's remarkable that even a person like Einstein, and there's many famous quotes by Ehrenfest also, he was saying that the second law, I don't remember exactly the framing, but is the only law of universal context that can never be overthrown. So it's remarkable because it's also at the same time it appears to be the most universal, but also it appears to be the only law that cannot be formulated in a universal manner, that doesn't have an intrinsic meaning when you apply it to an isolated system as we conceive of the whole universe. And let's also go back to time, the problem of time. So now people are used to think that the second law prescribes that time goes forward. So what I'm saying is that it's actually the opposite, is that time goes forward because that's just the only way we can conceive of our experience. And that explains the second law. So suppose, an egg breaks, right? Okay, and that is the second law of thermodynamics tells you that the egg breaks. And now the second law of thermodynamics also tells you that water falls, the water goes down, right? But is it the second law of thermodynamics that tells you this? Or is it the fact that waterfalls go down that tell you that the second law works? So in another way to say is, let's suppose that tomorrow we are at a dinner with friends and in our plate some egg unbreaks. It happens in front of our eyes. We see this spectacle. What do we think? Do we say, oh, look, there has been a violation of the second law in my plate? No, of course you don't say that. That's not serious. That's not like physicist attitude. Doesn't make any sense. You just say, oh, some physical phenomenon has occurred in my plate, which I've never observed before, and I have to make it consistent with the second law, with the fact that I only see things forward in time. So what eventually you will do, you will, you know, maybe it wasn't an egg, it was a joke, well organized by the guy who invited you, and maybe he managed to build a physical system that has some, I don't know, microphysics, microchemistry, microbiology, all perfectly tied up to undo this process. But then if you go into the details of the thing, it starts making sense. Each detail of the process goes forward in time in its own reference frame, and then the overall process finally gets back into the realm of the second law. So it's not that the second law prescribes anything in particular, and this I see as a practice in my work. I work on thermodynamics, and I came to realize that I cannot ask to the second law anything. It doesn't allow me to do any calculation. It doesn't allow me to compute anything. It's just a mental framework, a set of ideas that we keep in mind to, you know, to think about things, to keep track, to make sense. If we come up with a calculation that violates the second law, then we say, okay, we don't say we violated the second law. We say, okay, I must have done something wrong. There is something missing in my description. So in this sense, the second law becomes not a law, and here we're back to Hobbes. Hobbes has this idea of purified individuals, you know, having a social contract, and then the law is just, you know, this agreement by which they are subdued to the state. And of course, this is a myth. It's not true. Societies were not born this way, that it has no anthropological foundation, right? But it's a storytelling. Same way with the laws of physics, only the second law just is impossible to frame it this way. It doesn't do things like that. It's more of a moral, ethical principle. So it's a law not in the same of a contract, but of an ethical second law, of an ethical principle. Okay, so let me check the time because I think I might already be quite long. Let me try to skip on these and these as well. And let me just try to get to some finish here. So the point is, of course, I don't want to disqualify the second law. I just want to pinpoint the fact that the second law and the laws of thermodynamics play a different role in the construction of physical sciences than the laws of mechanics do. And this leads us to, of course, conceiving of science as a social practice. Okay, so of course scientists create communities, they work together, they share myth, they share narratives, they do work, they have a method which most often is not actually the way they work, but it's a storytelling of how things should be done, at least in principle, to convey credibility to a discovery. I cannot go through these, but I want also to discuss about difference between complexity and holism, separation between plan and execution. So a plane of discovery and a plane of justification, you know, we tend to think that they should be separated because this gives credibility to a discovery. But then in practice, when you see scientists at work, they are never actually separated. And it's a very subtle and complicated manner to distinguish between what is actually an experiment or a discovery and what is the construction of the conditions upon which something can be discovered. Okay, I think you as philosophers, you know these things. But finally, just to come to a punchline, the second law as an ethical principle, I think it's conceiving of it as an ethical principle can be used as an empowerment tool. It's not dangerous, but actually it forces you to think in a more active way of how you actually use, well, first of how you use energy, and second of how you use models into complex environments, simple models into complex environments. I think that's the way it can be used. Yes.
Sorry, we have another question. Before we
continue. Yes, sorry. Yes, okay. Okay, I can spend a couple of words on this. Here I completely skipped on the modern way we conceive of thermodynamics, but and here I'm. So my own work as I do, well, the field is called Stochastic Thermodynamics. I must say this way of calling it sometimes is just a rebranding of old concepts. So exactly Maxwell, Boltzmann, Einstein, etc., etc. Okay, all bringing in the idea that thermodynamics is a theory of information. Basically, it's the theory of. So if you say how good is energy, what's the quality of energy, you're posing a question of what can I do with energy, and then what information do I have about a system so that I can use it to perform some operation. So this is levels of conceptualization. And interestingly, with Shannon, there has been a merge between the concept of entropy and the concept of missing information. Okay, so here I can mention this interesting issue that arises, and that, you know, I cannot give you a full overview, but it talks with everything that I've said so far. If you define entropy, for example, so entropy in this case would be a measurement upon a probability distribution. So we have some variable, let's call it x, which takes some values x. So for example, if you have a coin, x could be head or tail, right? And you have a probability distribution. So the probability that x takes some value, okay? So for example, it could be that P of head and P of tail is 1/2, if we think that the coin is fair, right? And then the entropy would be measure of the distribution is just sum over the values P of x log P of x, okay? But now if you go into serious axiomatic definitions of entropy, or trying to make sense from a mathematical point of view of this object, you realize, so this seems to be objective, you know, given a distribution, this is given. But actually, you soon realize, if you try to think deeply, even from a mathematical foundation point of view about this kind of object, you realize it doesn't make much sense. It should always be written as I think there's a minus here. I don't remember. Anyway, you should always write something more like sum over x, p of x log p of x relative to some other p prime of x. So now I won't go. This is called relative information. And the important thing is relative here. So you start realizing that there is no absolute way of collecting data. There is no intrinsic, there are very specific systems for which offer a very isolated, precise experiences. For example, the coin is pretty natural to assume that it's head or tail, right? So you're conveyed into the idea that probability is an absolute thing. But then if you actually think of how we build probabilities in real life, how we assign values to data, how we decide how to collect data and give them an amount or associate to them values, I mean, we are nowhere close to the idealized concept of the coin or the die. We are in a situation where we have to make some a priori assumption, and then we have to perfection it, okay? So this goes into Bayesian probability, subjective foundations of probability. You can read Keynes. But in particular, I highly suggest Bruno De Finetti, Italian school, who really thought deeply about the fact that we are taking a perspective on things, and then we refine our concepts. But then, if entropy becomes a measurement of missing information with respect to some prior probability with some perspective, how do we make sense of it as a physical law that has to prescribe things that should not be dependent on the observable, right? That's the point. And this is one of the arguments. I can give you a reference to one of my own papers. I've been thinking about this a lot. While entropy in itself, entropy of the universe in particular, does not make sense. Is not a physical law. Is not the same kind of law as we tend to think physical laws are. But still, it doesn't mean that everything is relative to everybody and that every perspective is the same. It's just that you have to be careful when you do things, not to conceal the fact that there is a perspective behind. And if you think that there is no perspective, if you think that you're just observing objective data, then you're lying to yourself. Then you're being naive, and then you're probably doing damage. Which leads me to the conclusion, which is precisely this, is like the second law can be a motto. It can be printed on t-shirts. Second law, time goes forward. And this is, of course, the worst way. Or it can be taken for what I think is the most precious value of it. Precisely because thermodynamics is not a modern science, it has a lot of value that modern science is not able to translate into modernity, which is ethics, shared narratives, being able to, which is myth in the end, myth creation, mythopoiesis. So I get to myth because when you read that science and myth title, you would think, we as scientists tend to think that myth is bad. But no, myth is a fundamental ground install of human communities, fundamental to share values, to agree on what is important and what we have to focus on. So in this sense, I think the second law and thermodynamics can play a role in modern science, which is not in the sense of modern science, but is still useful to go forward, especially because we're going into an era where, of course, using energy and complexifying this course and trying to trace back the details of what we are doing is going to be extremely important. And we don't actually need any preconceived idea of what the scientific method is as a rule, but we have to share some values on what we believe. But of course, it's a very slippery road. Here I just show you. I didn't talk about reductionism and thermodynamic cycles. There's not much time for that. But here is some news about hydrogen train in Germany. And I'm sure somewhere here they will say that this is a zero emission train. Yeah, exactly right. Especially in Internet, presented a zero emission train at Innotrans, a railway industry. Now, how do you think it's possible to build a zero emission train violates the second law of thermodynamics, right? So what can we use the second law of thermodynamics? We cannot actually use to do calculations. That is useful, but it's just a reminder. If anybody comes around and says, oh, look, I built a zero emission train, then, you know, something rings in your head and you say, no, that cannot be true. And then you set up to find out what's wrong with it. So in this sense, the second law works as an ethical principle. It makes you aware that people are making bad claims, but then you have to start an inquiry into the specific problem. And the second law does not really help you in doing that. It doesn't tell you where to look at. You have to just go into the specific system, which is different from any other system in the world, and just bang your head into the wall until you find what the problem is. And for that, all of the other physical science, chemistry, etc., comes handy. So, for example, the zero emission train, of course, is hydrogen. But what's the problem? That hydrogen on planet Earth is all burnt already. It's burnt. And its burnt form is called water, right? And so you have to produce hydrogen. And to produce hydrogen, well, that's a cycle, right? So hydrogen burns into water, and then you have to produce hydrogen. You have to couple it with some other cycle, which probably will involve some fossil fuel, right? Somewhere else, and probably many other things. You know, you have to also produce, I mean, hydrogen is not easy to transport, so you will have to produce materials that can stock hydrogen. So there's a lot of material balances, then there will be a lot of other political cycles, social, economical infrastructure to build. So, and all of these talk to each other in a very complex manner, right? So what's the problem here is that people, you know, just take this part of the story. This part of the story happens to be in a very rich Western city called Berlin. And then they say, oh, look, we have a zero emission train in Berlin. Yes, of course, because this other part of the story actually happens, I don't know, this happens in Africa, this happens, I don't know, etc., etc., etc. So the zeroth law helps you trying to complexify and trying to keep pace with the fact that no such claim can be sustained. But unfortunately, it's not as powerful in telling you exactly what is going wrong. There you have to call the experts and trying to figure out on your own by using all the details that can possibly go into the problem. So finally, we are up to the conclusion. This calls for a big involvement of scientists into society and of society into science. So the moment when we say there always is a perspective in data collection, there's always some bias, then as a scientist, you cannot just answer, I'm doing my job the best way possible and I'm being objective, because that objective part does not exist. If you think you're objective, you just don't know what exactly you're doing. On the one side. On the other side, we also have to rebuild trust in science, because people in science do know a lot of things. Details that are very subtle sometimes, are very specific, but are extremely relevant. Sorry, there is a tractor passing by at the moment. And these details are not just technical details, but they may be the main thing in deconstructing the particular technology, the particular social context of that situation. So we have to find ways to bring these two things together. And okay, so maybe now in the conversation I will have time to more freely discuss a little bit about these projects we run with Extemporanea Science Ground, which are precisely, so this is a collective of young guys, about all, I'm the oldest, I'm 40, and the others are mostly below 30. We are about 20, 30, maybe 40 people, I don't know now. But, and we do all sort of activities. We read books together, we discuss, we do workshops in schools. We try to write collective articles. We tried podcasts, interviews, just anything. We want to have fun, and we are not we're not doing anything in particular for work. Well, and I think it's what is needed is precisely to create intermediate bodies within science and society, because society does not, science does not have a proper critique. For example, you know, if you read a novel, then you can read the whole critical debate about a novel or a movie, but if you read science, there's just either the scientist's voice or some lazy journalist, or you have on the opposite side of the spectrum, you have this radical criticism or refusal of sciences that just doesn't work as well. So we want to try to create the conditions for a more complex and nuanced conversation on science that takes into the debate all of the philosophical, sociological, anthropological, etc. variables. But maybe before I go into more details of this, I conclude and I wait for more questions and see.
Okay. We start the discussion. We open up the discussion. So if you have a question, you can raise hand as Goran did, or you can write it in the chat. So please, we have one from Goran Rujević. Goran. You have the stage.
I'm sorry. Is it my turn now? I'm having slight difficulties here in connection. Hello, everyone. My name is Goran Rujević. I'm of the University of Novi Sad. And Professor Polettini, please let me say it at the beginning. This was an utterly riveting lecture. I've enjoyed every second of it. And I have 2 points that I'd like to discuss shortly. One of them is just a check to see if I understood the central idea that you had, and the other is a veritable question that I'd like to discuss. So the first one regards the the issue that you mentioned towards the end of your lecture, where you described those scenarios with the egg and the waterfall. And in the very beginning, I was slightly taken aback because I thought you were describing psychological impressions, the way how people perceive reality, egg breaking or water falling down in a waterfall. But then after you explained the connection of these between the phenomena and the very second law of thermodynamics, I actually think I understood what you were mentioning, and I just wanted to check if my interpretation would be correct. When you mentioned that the second law of thermodynamics can be understood as a motto or as an ethical rule, would it be correct to interpret that idea and say that the second law of thermodynamics is actually a kind of a tool, sort of a thing that we use to bridge our intuitions of the world and the way the presupposed objective reality actually works? Would that be a correct interpretation of your point?
Yeah, definitely. So, I mean, if I have to say it really plainly, I think it's just my grandmother knows perfectly well that you cannot just have something for free, right? That's just the way we say it in physics. The same thing. It's an ancestral mode of thinking, but it's important. It has to be there because we lived in a society where we have forgotten about that. Where we consume too much and we don't keep track of where the things that we consume go. And to my grandmother, it would be completely inconceivable, and she had no need to know of the second law to know it, but they do the same thing. They do the same thing. And on the other hand, you have to take it for what it is, precisely to avoid holistic, mystical points of view. I think sometimes physicists are being mystical and they don't realize they are being more religious. Even, especially those physicists who tend to criticize religion the more, they turn out to be mystical themselves, to be religious. Like Richard Dawkins is full of beliefs. It's incredible how religious he is for being one pundit who keeps, banging on theology and religion. But I mean, the moment you say the second law explains something, you are making you're not using it as a tool anymore. You're using it as a justification for power, probably for relations of power. So it's a tool of concept, not very powerful, but it keeps you fresh. But so another point of view is, when discussing these things, especially with my friends physicists, they think it's dangerous to talk about these things, because you may give people who don't believe the second law some argument, right? Well, first, I think people who don't believe the second law and try to build their own energy resource at home don't threat science. Science is not threatened by these guys or by the guys who think that the earth is flat. I actually think these guys are doing the correct thing. They are asking questions. They're doing their own way. They don't know. They are not well learned, definitely, but they are asking questions. And they're restarting science. In a way, science started like that, right? People asking dumb questions and making dumb experiments and then coming up with better questions and better experiments. So, and definitely science is not managed by these things. Science is managed by many internal enemies and external pressures, conflicts of interest, name one, but definitely not about people who try to who think that second law doesn't work. And second, the other thing is taking the second law too seriously can lead. So on the one side, I want to criticize reductionism, and the second law is useful to remind that you cannot reduce everything to just a single process. Like the hydrogen train in Berlin is not just one single process. It's a complex environment of processes, each one interconnected with each other. So you have to dispense with strict reductionism, but on the other hand, you don't have to fall in the opposite side, which is saying, you know, reality is so complex, everything is so interconnected, everything to each else, and that we just give this holistic idea that everything just breathes as an organism, organicistic, you know, idea that everything, because, well, that's just another form of reductionism. You're giving up on trying to explain things. You just reduce everything to something, and you say, okay, I cannot say much more, and this is dangerous. Again, because it can be used by corporate power. So, for example, if you go see the Gaia hypothesis, you know, of Lovelock, the idea that the Earth is a one self-regulating macro system which lives of its own life. It's fascinating. It's interconnected ecosystems, but it's not empowering. It's not giving you something to do, and it's actually giving the oil industry an argument to not do anything. You know, because the Earth self-regulates, so why should we do anything? And actually, and it's interesting, James Lovelock was financed by ExxonMobil when he wrote that research. So, and we know this. So it's, you know, concepts can be used in one way or another. I'm just saying, let's try to make the most of the second law without exaggerating its importance, but also keeping in mind that it can be used as an empowerment tool.
After all, if we somehow manage to build a perpetuum mobile machine, well, I'm sure every one of us here would be a happy camper indeed. Now, great. I would like to ask another question. Alexander, would that be all right? Now, thank you. The other question would be a little bit more on the speculative side. You've mentioned several times in the beginning of your lecture that if we should take the universe as a totality, as an absolute system, then time would in essence be lost, correct? I would just like to hear a comment from you. Why would that be necessarily conceived as a bad thing or something that we do not want? Because so far in the history of science, we've already given up on so many intuitions and concepts that we've held dear for such a long time. We've given up on phlogiston, we've given up on ether, we've effectively given up on simultaneity as we intuitively understand it. So why not simply also give up on time?
No, I mean, we could try. It would be definitely a challenging thing. It's fun. It's beautiful when you actually see in quantum gravity, in that particular program of quantum gravity I was mentioning, loop quantum gravity. It's really fascinating because you work out the equations of motion, and because they are based on general relativity. General relativity has this beautiful symmetry between space and time, and it's very self-consistent theory. And you come out with this Wheeler-de Wit equation where there is no time, it's hc equal to 0. The point is, now what? What do we do with it? What do we calculate? That's the point. The whole community of the loop quantum gravity community went through a crisis when they found out that they were based on the Wheeler-de Wit equation, because the point is, what do we calculate now? I mean, we are here now, and we have to do an experiment. What do? We don't even have what do we confront it with? You know? So conceptually, it's very fascinating. It's beautiful. This Julian Barbour I mentioned, I think, is obsessed with the idea of giving up on time. And from a conceptual point of view, I think it's a fascinating idea, but it just doesn't do much. It doesn't allow you to do much in the real world, because we are here when we have to do something. So well, sometimes we don't have to do so. But the point is, I think we really have to, science has to face a change in the way we conceive of even the scientific method. You know, most of the scientific method, the way it has been thought in the 20th century was after Popper, Kuhn, Lakatos, Feyerabend, and then there are, of course, other authors which are less known, but probably more important. But most of these contributions were shaped on physics, They even, Popper, Kuhn, they all had in mind physics. And physics has very much this program of isolating systems and then reconstructing reality out of that. But now we are in a completely different time. We are facing and this also carries to other sciences. So, for example, the moment we have a pandemic, virologists speak up, right? But the virus is a different thing if you see it from a virological point of view, which is the equivalent of isolation, not like it's a lab conception of the virus. You put in a laboratory, you remove it from society, and then you try to come out with conclusions. So, for example, with HIV virus in the 90s, for a long time, virologists were convinced that HIV could be passed by kissing, right? It took a lot of popular initiative to convince that the HIV virus should not be interpreted by virologists, by epidemiologists, because epidemiology is a completely different science. It has the scientific method that we study and learn has almost nothing to do with most of the sciences that are becoming important right now in our world. Epidemiology, geology, the earth sciences, climatology. There's almost nothing in them which resembles the way virology or physics, laboratory physics work. So we have to really, and even, so my point is just these ideas, this training with ideas of isolated systems is fun. It's a beautiful game. It leads to very interesting concepts, but it's just over. It's not interesting anymore for the kind of problems that we are facing tomorrow. It's not interesting. And even the moral dilemmas that certain theoretical philosophy brings you to think, right? We have all these thought experiments, philosophical thought experiments. There's a train running down, and if you keep it going, it will kill 6 people. And if you pull a lever, it will derail, and kill only 1 child. So what do you choose? Now you have to make a rational choice with moral dilemma. So on the one side, you kill more people, but you don't do anything. On the other side, you take some initiative, but you have to make a moral judgment on who you want to kill. Yeah, okay, it's fun to think about this thing, game theory, very rational way of conceiving of intelligence as problem solving, as very well-defined situation. But we are not in that. It's nowhere close. Yeah, it's not only we are not in that, but if we only keep on thinking on these things, we may impose this way of conceiving of society into society. I mean, the social dilemma that we pose is because there are programs, for example, self-driving cars. Everybody is around machine learning for self-driving cars, and even philosophers now think about social moral dilemmas with self-driving cars. But the point is, the moment that you decide that is important, you're also forcing a program of structuring streets and structuring the policy making on keeping on with cars, while we need something else. We obviously need to get away from cars and into another way of conceiving of people moving. So that's what I'm saying, is that this way of thinking of isolated problems in vacuum is fun. It can lead to very beautiful conceptual. There's lots of smart people out there. It's just not what we are into in the next 50 years.
I see. Thank you. Thank you very much. This was a great lecture once again, and I shan't be hogging the stage anymore. Thank you both, Professor Polettini. Thank you, Alexander.
Thank you, Goran, very much. Now we have Philip Strasberg. I guess that's the pronunciation, but Philip will correct me.
No, pronunciation was perfect. Thank you.
Oh my goodness.
So hi, Matteo. Let me explain. He invited me to attend the lecture. I'm also a physicist working on similar topics. I'm not a philosopher. And I think he knows that we agree on many technical aspects and many things he said. So I just want to mention that. But I don't want to talk about technical issues. I want to rather understand where is the departure between our opinions? So do I get it correctly that you really don't like this kind of purification postulate you talked about, so that you really say, oh, I don't want to take this heavy back, so there's something like, you know, that I can define a system somehow which, you know, which has no external perturbation. So I mean, I think this is all where you build on, no?
Okay. I think I'm running out of battery, so if you excuse me, 1 minute, I will be right back.
Sorry, Philip, but you already know Matteo, so I guess it's...
No, it's no problem.
So, sorry. Okay, we almost solved this problem. And yeah, thank you very much. Okay, so Philip, you are asking, where do you think is the point of departure between me and you in our technical discussions?
No,
and and the fact that I don't like purification. It's not that I don't like purification. I mean, it's great. It worked. It did lots of useful things. We can, you know, GPS technology works on general relativity, and what I'm saying is just, I think thermodynamics intrinsically does not even consider. Okay, on the one side, I think purification is not completely possible. And we know the obvious example is quantum mechanics, okay? So it has to satisfy a different set of axioms which are not within the theory itself. And then let's not even go into the issue, you know, people trying to figure out if it's actually a different set of axioms or if you can still conceive of them within the theory itself, etc., etc. But at least, let's say, the motivation is at least that of trying to purify, to create situations where you know that things will work that way up until you have the problem of measurement, and so you do. Celestial mechanics, electromagnetism. But with thermodynamics, I just think from the very start, it is based on the assumption that you cannot purify, that you cannot do. It's true that thermodynamics has some specific systems that in a way are the canonical systems, like the ideal gas or the Ising model and stuff like that, which more resemble the mechanical theories, but for what is the scope of thermodynamics is just, the scope of thermodynamics is basically every system, so it doesn't have that same level of clarity. But it may be just an historical situation. Maybe that tomorrow thermodynamics just finds the set of systems to which it applies, and we call. Also, it also depends on disciplinary definitions. If we talk about thermodynamics the engineering way, then thermodynamics is just about machines. that's a very well defined, very well known setup. And in that case, yeah, it's a phenomenological science. But the way physicists conceive of science, even Einstein, the way Einstein used thermodynamics was more of toolkit for thought, but not exactly like, not the same way that electromagnetism works. Like you take electromagnetism, you solve the equations, and it spits out some numbers. Einstein was really using thermodynamics in most of his famous 1905 papers. It was both in the one in the laser and Brownian motion and well, I don't remember, the photoelectric effect, Brownian motion, and something else. In all of them, he was using thermodynamics as a sort of, conceptual tool that he could use, and then he was brilliant, of course, and he could then translate it into the specific problem. But the translation was not automatic. It's not given by the equation. It's just that you have this beautiful intuition conveyed by thermodynamics. Also, I think thermodynamics has never really... So I think in this process of purification, it's important that you, at the same time, you define the domain to which you apply things, and then as you restrict the domain, the law comes out, the possibility to unify those things by a law. Thermodynamics has never really done this thing, right? It's intrinsically without a proper domain. Now maybe with Markov processes, we are trying to define better. But okay, this opens up many other questions. And the other thing is important, which I didn't have a chance to talk in the talk, but in the purified sciences, even if we know that it's not true that the method works the way that the guys who made the theory of it works, but at least in principle, there's an idea of a separation between a plane of observation and a plane of justification. So this is important. It's never like that, but then at least people try to do it. So for example, gravitational wave community, they won a Nobel Prize 4 years ago. There's a sociologist of science, Hattie Collins, who describes the way they work and the way they make sense of the signal that they receive. So they receive this very weak signal from the universe, and they have to figure out whether it's a gravitational wave or it's just background noise. And to do this, they have to clearly separate two moments in their analysis. There's a playground model. There's a model where they play with the models and theories and formulas, because it's not just that you receive the signal and you observe it. So you receive the signal. This signal has some features. And you have to decide how to analyze it. But if you decide too much, you may be observing a signal even if it's just noise. And if you don't decide enough, you just observe noise because you don't have tools to see it. And to justify the fact that it's either signal or noise, they have to clearly separate a moment when they decide how they are going to analyze the signal, and then a moment when they actually do the analysis. And these have to be, even from a social point of view, they have to be very separate moments, coordinated by different people. These people don't have to talk to each other, and they go through lots of procedures to, make sure that this separation is made. With thermodynamics, many important theories in physics have had this. General relativity has had this, quantum mechanics has had this, celestial mechanics. Thermodynamics never had this. The machines, the experimental setups, the examples that we use to illustrate the second law or the laws that we use, and the theory have never been untied. And we never even tried to actually, So it's still a young science. It can happen that 200 years from now, 100 years from now, we are up to that. But so far, I still see it as a not yet modern science.
I mean, to what I agree to is completely that thermodynamics is a very different theory from classical mechanics and quantum mechanics and electromagnetism and all that. But I mean, the argument I actually wanted to throw in was something like Occam's razor. So what I'm claiming is that when I buy this purification thing and that thermodynamics works for an isolated system, I need much less axioms to make sense of observations and things which go on. Whereas from your perspective, you say, oh no, I don't do this. I only stay within this reduced paradigm. For me, you need way more axioms to make then sense of observations. And then my question is simply, shouldn't we use a simpler theory where you need less axioms to describe what's happening? No? Or would you say you would completely disagree and you use less axioms? This is, for me, the point is I'm missing the point where with your philosophy things become actually simpler. No, I mean, why should I buy it? If you're on a market and you say, look, I have this philosophy, but actually everything is super hard with that, why should I take it? I don't know. It's a long question.
I don't want to sell it. I want to make it. I want to be realistic as what we actually do even in my job. You know, when I have to review papers in stochastic thermodynamics, and I see people will come out with an object that they call a fluctuation theorem, and most often this is not even a theorem; it's a definition. And sometimes they don't see the loophole in the argument they are making. And I don't think it's just because they're not good scientists. I think it's because there is a fundamental issue there, is that there is no independent way of defining entropy production apart from that thing, that measurement of irreversibility in that case. So, but I don't want, yeah.
Maybe I can, because my question is somehow related to that of Philip, so maybe you can answer it both at once if it to maybe save time. So I will go back to what I know, my field, and that is philosophy. So the Leibniz said some similar thing about reduction. He says we always lose something, and we are not aware what we lose in the reduction. So, for example, the knowledge is a construction in a way that you somehow relate the elements. You have some elements and you relate them, some spots, and if the relation of them is correct, which you can check by empirically, then you have some kind of knowledge. But the problem is, it is never, the process will always do something. It is never... for example, you have one spot X that's connected to a spot epsilon, and we have some relation, and based on that, we have some conclusion or a law. But the problem is the X is connected to set X1, X2, or whatever, and the epsilon connected to many other things. So the problem is not like Kuhn said, you cannot build, the theory doesn't always build on the back of itself, but somehow the construction completely changes with some new relation that you haven't been aware of in the first approach. So my question is it always, and I guess this is, do we always lose something in reduction? When Philip says why should I buy it? Why complex and not simple? Why not less axioms? Why more axioms?
No, we definitely...
Is it somehow related to this? Is it we always have, as a world is always expanding or not, it doesn't matter, but we always have some new elements that we are not aware of. So you always have, axioms cannot be defined forever. It is an ongoing process, never-ending process of new elements that will change the construction, the first construction itself. And the second question is it a never-ending process? How can I make a claim by, more precisely, when do you become aware of the perspective you have? When you say we must be aware that we may have some perspective and that we see not the thing that it is, but just some reduction part of it. How can I become aware of it? If I know that it's a never ongoing process of learning, when do I post some law or effect or something that that society must learn from science?
Okay, I try to answer both because it's already quite a lot of stuff, and I want to keep focused. So I think I can answer both in a way, but the point is, of course, reductionism, you lose something, you lose a lot, of course, but it's important. It's fundamentally needed. If you renounce reductionism, then you cannot say anything, and then it's not interesting. The point is, does it work? So the point is also, is not true. So the story, the reconstruction of Feyerabend of how Galileo deals with friction is very interesting, because it's true. On the one side, we have a new form of reductionism, which explains ballistic, for example, right? The motion of heavy objects, of shooting, etc., etc. Acceleration explains that better than velocity. But then you have to, okay, so you're making a reductionist step. But then it's not that the moment that you reduce reality by that, you renounce to everything else, because then what you do, you attach all of the rest of reality that does not fall within the reductionist approach, you attach it with the glue, with extra assumptions. So you make up friction, or you make up lots of stories. Galileo was observing the moon and was observed with the, how is it called? I don't know, the tool, and it was observing certain things, but then certain others were not true. And it was just, fixing a lot of, there's lots of fixes. It's not like there's a new theory that explains everything that was before and progresses. No, there's a new theory that explains better a few things that were not understood before, does not explain a lot of things that were explained before, and it has to patch everything together. But it was just the right time, the right place. People were tired of these Latin speaking philosophers who claimed that all of the knowledge was on themselves. It was a time when people who only talked in Italian were saying, we have some knowledge, we can contribute to something. And so there was a social, uprising already, and Galileo was just the right person, right time. But if you actually see how his new reductionist approach worked in the beginning, it didn't work well. Even the Copernican model worked very badly for a long time. It took a long time to adjust it, to explain. The Ptolemaic model was actually better for doing calculations for a long time after the Copernican and the Kepler contribution, Tycho Brahe, etc. So this means that it's not that you lose a lot with reductionism, but it's not lost forever. It's then you glue it together. It sticks around, and I think thermodynamics in a way has been doing this in physics. It keeps on taking into the picture. It's useful for all those things that just don't fit within electromagnetism or mechanics, quantum mechanics, etc. Thermodynamics is the repository where you can still talk of the rest of the world using a physics jargon and keep it into the wave, into the motion until some better theory comes and eventually will help reduce at least part of those into more fragmented and separated things. So I think reductionism is useful. The point is, does it work? And reductionism works when it defines a broad enough set of problems that can be studied and which don't boil down to one single. Doing the theory of one thing doesn't make any sense. It's better to learn to use the thing. So you have to be inclusive enough and reductionist enough. With thermodynamics, it can be that at some point we decide, okay, this is the class of system that this theory with reductionists, etc., really describes well, and we can do experiments with that, and etc. But I think we're not yet there. It's just maybe it's just too young as a theory. I think it also has a lot of jargon that comes from preconceived ideas in the 19th century. We should just give up with many concepts that we keep up just because it's and you know, also Philip knows very well, there's a bit of everything in thermodynamics. Now we are trying to make it a more coherent and consistent framework, but until yesterday there's so many different laws that do not even talk to each other. You know, there's the first and second law, but then if you see the third law, it's sort of on a different conceptual plane, and then you have the laws of gases, and then you have the laws of radiation. But these are
now you're going into specific scientific stuff.
Yeah.
We have one more question for Srdjan, maybe for myself, and we have not much time. So if Srdjan can.
Okay, sorry for that.
Yes. Hi, Matteo. This is truly a fascinating talk. So I'm a sociologist, and I was just wondering, right now, when you mentioned Galileo in this example where, you know, you said something like down the line that the moment was right, the configuration, the social configuration was right. And that got me thinking about some specific stuff that's happening in trying to apply some of the complexity, developed complexity in sociology, which is also related in some way to thermodynamics, at least to some notions of entropy as far as I know. And that's the idea of the adjacent possible, the Kaufman's understanding of how innovations work. And I was just wondering, have you in your research touched upon this question? Because a lot of things that you were speaking about, like how much one of the premises of adjacent possible, if I understand it correctly, is the more you go into the particularities of a system, the configuration of a network, the more adjacent possible this shadowy near future opens up. So I don't know whether or not you have done some research or read something about it, or have you any take on how this relates to the main topics of your today's lecture? Thanks.
No, no, thanks. Very nice question. No, but I never thought about this. I know people who do. So if you want to write me, we can share some literature. I know people who work on these kind of problems and ideas, but personally, no, I don't know much. I want to say. Okay. Maybe just Alexander, I could just say one last thing about extemporanea and the project.
You can. We have 10 more minutes. It's just what you didn't answer, and I think that from sociologists and philosophic side will be interested in it. How do I know when the reduction is useful and when it is and when it can be criticized as a form of legitimation, as a point of power, as a use of power to legitimate an action or a system or a construction, social construction or whatever. So when it is a decision to say, okay, this now we will go with that, is a form of power, and when it is a search for knowledge, how
That's the $1 million question. I mean, there's no criterion. I mean, if it creates a better society, then it's good, and if it creates a poor society, then it's bad. I mean, it's really, I don't have a solution. The only solution I can offer is precisely this kind of process I go through with extemporaneous, trying to get scientists think that what they do is in society. It has, if you work on artificial intelligence today, you cannot just say I am doing research and I'm doing the best research possible. No, because any project in machine learning you're working on is part of some program. You have to understand what that program is. If you are perfectioning algorithms that recognize images, you have to know whether the collaboration you're working for is offering this data or these tools to companies who do image recognition for security or for military purposes. You have to know it. But there's no qualitative criterion. It's just it's very difficult. But I guess scientists have been a bit too in their own laboratory, and especially now we have, most peace activists. We had a very beautiful encounter with the peace activists from Israel last year, and he was complaining this. Most peace activists are from the humanities, and they do a good job. They try to help, but they cannot do much because they need scientists. Now if you take Israel is the second main producers of systems of control in the world, or of drones, and we don't even know what exactly these things can do. And if you're a guy from the humanities, you can just go as far. We need scientists to get involved into this kind of critical analysis, and scientists cannot just think that they are in a laboratory doing research. They're doing research within frameworks, but apart from that, there's no criterion. It's like I tend to trust communities. I think there's a big mistrust in what people can do when they self-organize because they have a common goal of being well together. And this leads to technological solutions, to conceiving of arranging things for them, maybe by algorithms or by. I tend to be more faithful in humans when they. But apart from that, it's difficult to tell, So maybe just one final word, because it would be really nice if somehow this conversation we started today could go on other channels and other tools. So I don't make a presentation of the full extent of the projects. And just saying, we just met over the weekend with the group, and we definitely want to focus more and more on activities, on workshops and activities with teachers, to try to experiment on new forms of pedagogical tools to discuss these things, even with children. So we have workshops on machine learning, for example, on computation, on language, and many other things. So this is the main activity, like the public activity that we want to experiment, and I can present it, maybe just send in an email about this. But in general, inside as a community, we are also starting this nice practice of reading books together and commenting articles and just sharing on specific topics. So we started with the Against Method by Portal Feyerabend, and now we want to move on to some other. I guess we will keep on talking about epistemology or related issues. And I guess maybe this could be an activity that can be experimented with a broader international community. So in case we could share some thoughts via Alexander and via the others who participated. Then maybe I just say we are involved in these scientific conversation activities, mostly in schools, and then but also we have a public situation in Mantova every year. It's a literature festival, which is also interesting because we're bringing proper scientific discussion into a completely different world, which is the world of literature, which is challenging and interesting, and also this offers a nice a nice situation, because it's actually in Italy. There's not many as I was mentioning before. There's not many intermediate bodies between science and society. There is no layered ways. And this has the implication that that there's not much liberty for discussing science. So, for example, if you're a scientific journalist in Italy, it's very difficult to discuss about conflicts of interest between, research institutions and companies. It's very, very difficult. So the point is, that to be able to be free to do that, you need new institutions which are intermediate institutions that can, back you up as an individual when you want to, try to go deeper into something. In the Anglo-Saxon world, there is a little bit of that, but not in Italy. And I think what's interesting of our experience is precisely that because we are hosted at a literature festival, we are in that situation. We are in a completely different context where there's a lot of freedom, because we are not directly involved in scientific journalism or scientific divulgation or propaganda. So we just like to do this conversation. We are in a safe space, and so we can be extremely open on the things that we propose. So maybe
thank you thank you very much for a wonderful lecture. It got most of us involved, and thank you for your initiative. I will surely propose to people from the institute, and whoever is here is welcome to write me if you want Matteo's email address or contact. I'm sure we can find some projects, platforms that can allow us to easily interact for whoever wants to visit Mantova, for example, or got involved in this kind of deal or job. So we keep in touch. I will look personally at possible projects that can relay, maybe institute and your organization.
Perfect. That's great.
Nobody has.
It was great to meet you. Thank you for all the questions. It was very interesting discussion. Ciao, ciao.
Thanks you all for participating. Ciao, Matteo.